Today I'm going back to the old way of recording. Sorry, I will be back on the light board soon, I hope, but was having issues doing my recordings for a while. So this will be a sort of normal lecture, although I've set up things where normally you should see the slides, you should see CZG session, and me. But that's not the important part, okay? So in particular, you'll have the slides and you'll have the CZG are accessible at the same time. Okay, so I'm going to start giving you some notions of how you can go about characterizing a graph. So we've looked at some properties of graphs. We've investigated some of them, but now what I want to do is to explain to you how you would go about sort of characterizing the properties of a graph. And let me, okay, so I have to be careful. So let me explain a little bit what I mean by this. So the main thing is that in today's world, graphs are absolutely everywhere. Okay, this is an important characteristic. There are many reasons why you would consider a graph. And it is often important to be able to compare those graphs, okay? To know if a certain graph is similar to another, or also to describe their properties, their shape, their characteristics. Okay, and that's a whole sort of field where a lot of research has been going on. I mean, it was mostly triggered by people working in the social network theory domain a long time ago. Actually, this really predates social networks as a sort of like Facebook and etc. This was used in particular to characterize the way interactions happened within businesses and the like. Okay, so this is not new, but of course now we have access to enormous amounts of data that are very often structured as graphs, and therefore there has been an enormous expansion of the work on that domain. But altogether, this is a domain where there's still an enormous amount of work taking place. Now, we could have a whole course, a whole term, or actually probably several terms, just in terms of looking at the properties. I'm not going to go that much into detail, of course. What I'm going to do is give you a few measures and also show you some applications, because I think this is a context in which really understanding how the computer can help you do work is really important. Okay, you have to understand where the mathematics is coming from and how you link the mathematics to the actual real world problems. And so what I'm going to do is I'm going to give you a bunch of measures, let's call them measures, and throughout I will be illustrating this with a variety of examples. So this first lecture is just a beginning. I mean, it sort of completes the previous lecture in the sense of time. So I am not going to spend a long time here, but I'll get started with the ideas. Now, I will point out that if you think of a graph altogether, the type of measures of structure that you're going to obtain, they are going to be of two major kinds. There are some that are going to be very specific to properties of the vertices. and others that are going to characterize the graph as a whole. And I will try to always make it clear whether a measure is relative to the graph itself, the entire graph, or if it is relative to a vertex. Okay, so, and you'll see what some of the times we'll be able to have the two, but it's going to be rare. Most of the time it's going to be either we're looking at a property of the graph or we're looking at the property of a vertex. So let's get started. And this is going to help you in the assignment that's due Thursday. So this is coming a little late. I was hoping to do this video earlier, but I have been having silly computer problems, and that has made things difficult. Now, in everything that follows all these measures, typically I'm going to think of about a directed graph. It can be a one graph. Some of my examples will be one graph. Some of them will be digraphs, so without the loops. Some of them will have loops. It doesn't really matter. But most of the time I'm going to talk about the directed version. If it's undirected, I will sort of emphasize this by writing the graph as consisting of vertices x in a set x and edges instead of arcs. Okay, but most of those measures that I'm going to talk about, they have a directed and undirected version. I will sort of indicate what the difference between the two is. The first sort of important notion that we're going to see is what is called the geodesic distance. And that's going to be fundamental in establishing quite a few properties. So the geodesic distance is if I take two distinct vertices, x and y. Actually, they need not be distinct. They can be the same. But if I take two vertices, x and y, I call geodesic distance the length of the shortest path from x to y. And I will write x, y equals the distance from x to y equals infinity if I cannot find such a shortest path. Okay. So that means if my graph is not connected or strongly connected in the case of a directed graph, then I am going to have trouble finding, I'm not going to have trouble finding, I am not going to be able to find a path between two disjoint components. And that means that we'll say in that case that the distance is infinite. And the length of the path, remember, is the number of arcs that you have to follow or the number of edges that separates two vertices in a path. In path is the directed version, but it would be the same with a non-directed version. You would count edges. So I will point out for the assignment that you could also think about other distances. And those cases where we have a graph that is weighted, where the edges or the arcs have a weight, then the distance might be the sum of the weights along a path. And in that case, the shortest path would be not necessarily the one with the least amount of jumps, but it could be the one with the least sum of weights. Okay, so the analogy is that if you're thinking, and that is important in your assignment, if you're thinking about the geodesic distance, this is simply amounts to taking a distance equal to 1 for each arc or each edge. Okay, so if I say that the weight of each arc is 1, or each edge is 1, then I have the number of jumps, so I have the geodesic distance. So the geodesic distance is a particular case of a distance in general. Okay. Now, if I look at this graph, which should ring a bell because that is the graph that is in assignment 9, I think, then here I can look at the distance from x1 to x2, for example, and that would be 1, because I have to follow one edge, one arc, sorry, to go from x1 to x2. The distance from x1 to x3 would be 3, because the shortest distance from x1 to x3 it's 2, sorry, it's 2. So I can go from here to here in 2 jumps. I can also, of course, do something like this, loop around and etc., but that is not the shortest distance. The shortest distance is between x1 and x3 is going through x2. And so I can get this matrix, which is actually the matrix that I'm expecting you to find. So here you have a big hint by using Dijkstra's algorithms. First of all, let me point out, I'm not entirely sure how you say that person's name. Yeah, well, I remember hearing it, but it's definitely not the way I say it. But this is a well-known algorithm which allows you to pass through a graph like this. And so you see here, I have not counted the loops. So this is a distance that the self-loops, the loops on x2 and x6. So this is a distance that ignores loops. Because here I could probably say that the distance from x2 to x2 is 1. But it is not considering distinct same vertices. You can see that from x1, for example, I can go back to x1 in 1, 2, 3, 4, 5 steps. But this is not appearing here in this matrix. The matrix is ignoring this. And I'll just point out something for the computer part of the assignment. I am asking you essentially to produce this matrix. And I will point out, and by programming Dijkstra, but also by looking at trying to find the equivalent function in R, which I'm not going to show you right now. I mean, I'll put it up later once the assignment is done. I'll just point out that the function you'll find in R has an option that you'll need to manipulate in order to find the matrix that I have here, because the function by default treats the arcs as edges, so it doesn't consider orientation. Well, I mean, it considers orientation, but following any direction. So you'll see there's an option that you'll have to manipulate if you want to follow the edges, the arcs outward. Okay, that's a sort of hint. Okay, so this matrix here is giving me the distance on each row from the given vertex to all the other vertices, and that's the minimal distance. Okay. So if I look at that whole matrix, I have a property of the graph, but if I look at each row in the matrix, I have a property of the vertex. Okay, so the first row is vertex x1, second row x2, etc. Again, I mean, as I said, this is going to be important. Just for illustration, I will sometimes do this just to show you the difference. I have here removed that arrow from x5 to x1. And so I have made, so that graph was connected, strongly connected, and this is something we'll come back to later, okay? But that graph is strongly connected, this one is not. And so here, whenever I am past x2, I am going to find infinite lengths, not for all vertices, but for example, going back to x1, because if I'm in x3, I have no path back into x1. And therefore, going to x1 or x2 has an infinite distance. And so has x4, because I can't go back down this arrow, and so this is infinity. Okay, so you can see that in the disconnected case, we have something that is going to include a certain number of infinite distances. Now, one very important quantity that we get from that matrix is what is called eccentricity. So, and that's a vertex property. Okay, so each vertex can be characterized by what is called its eccentricity, which is the maximum of the distance to all the other vertices. Okay, so E of x, typically that's how it's denoted for a vertex x, is the maximum for y in the vertices, but y not equal to x of all the distances. And that tells you, if you think of a graph as representing, for example, how long it takes you to go somewhere, that tells you what is the longest, shortest path to all the other vertices from the vertex you're at. So essentially, if your eccentricity is low, you have a good access to the rest of the graph. Okay, because you can be in any other vertex in a short number of jumps. Whereas if your eccentricity is high, or infinite, for example, if you have a disconnected graph, then you don't have access to these places. Okay, and so here I've illustrated in the matrix below the graph what the eccentricity is for the different vertices. So x1 can get to all the other vertices in 4 steps or less. This is what this means. x2 can get to all the other vertices in 3 steps or less, and so on and so forth. And there's no reason why the maximum number is unique. And you can see that on the last row, x6 can get to x3 and x4 in 4 steps or less. That's the maximum of that distance. So it takes as long to go from x6 to this one or this one. Here, because here I have a bifurcation after x2. So it takes as long to get to these two. Okay, so eccentricity, the lowest your eccentricity, the more access you have to the rest of the graph, and the highest your eccentricity, the less, the longest it takes you to get to the rest of the graph. And this is important to define some properties that are now sort of both vertex related and graph related. So on the vertex side of things, we call central a point, a vertex, so, that has the smallest eccentricity. And we call radius of a graph. So now this is a graph property. So a central point is a vertex or a set, like a given vertex. If it has the smallest possible eccentricity, it's a central point. And the radius is the minimum of the eccentricities. Okay, so it's denoted rho of g, which is, of course, is going to be annoying when we are talking about spectral radii as well, because that's also the notation for spectral radii. But that's it. Okay, so the radius of a graph is the minimum of the eccentricity. And finally, the center, which I actually should have put above, the center is the set of vertices that are centers, central points. Okay, so let me go back to our example. The minimum of the eccentricities is for x2. It was 3, and so that is the radius of that graph is 3. x2 is a central point. It is actually the only one. And the center is the set of central points. And in that case, it's only 1. And so it's x2. Okay, the set with x2. Okay. Now, if we go back, if you remember, we had roots and trees and arborescences. Now, if you take a vertex x0, it is a root if there is a path from x0 to y. And we saw that a graph has a root if and only if it is quasi-strongly connected. I'll come back to quasi-strong connectedness and so on, because these are properties of the graph also that we're going to look at, but we've seen that already. Now, so if we have a central point, what that means, that central point has an eccentricity that is finite, okay, it's less than infinity, if and only if the graph has a root, and that is equivalent to saying that G is quasi-strongly connected. Okay, so when I look at my graph, I am going to have a central point with finite eccentricity if and only if it's quasi-strongly connected. Okay, and an important consequence of that is that if I have two central points in the graph that is quasi-strongly connected, then those two central points must belong to the same strongly connected component. Okay, and we'll come back to that. Okay, and so we get this result, which I'm not going to spend some time over, but that might be interesting. This gives you a lower bound for the radius of the graph based on the order of the graph and the maximum of the out degrees of G's of the graph. Okay, this gives you a sort of way to compute what that maximum, what the minimum of the eccentricities must be. Now, at the other end of the spectrum, in terms of graph property, we have the center, but we also have the periphery and the diameter. So the diameter is the maximum of the eccentricities. Okay, so we call delta of G, or we write delta of G, the maximum of the eccentricities. And now, delta of G finite, so if I look at all the eccentricities, if they're all finite, this means G is strongly connected. And if I go back to this graph, which I disconnected, you can see here that I have infinite eccentricities, okay, because I'm looking at the maximum of those values and for each row. And so each row that has infinity in there has infinite eccentricity. Well, what that result says is that this means that the graph is not strongly connected. Okay, so that's an equivalent way of seeing that we don't have strong connectedness. And now, once I have a diameter, I can look at a set of vertices that have the same eccentricity as the diameter. And so if you recall this example that I showed here, you can see that those two vertices, 3 and 4, x3 and x4, have eccentricity 5. So the diameter of the graph is going to be 5, and the periphery of the graph is 3 and 4, which is, I think, what I wrote here. So you can see here that I've highlighted these two rows because they're the ones that comprise these two largest eccentricities. And so the diameter is 5 and the periphery is x3 and x4. So x3 and x4, what that means is they're on the periphery. I mean, they're not clearly not on the periphery, but if you think in terms of axis, they're the two locations from which it is the longest to get to all the other possible locations. Okay. So these are vertices that have low connection with the rest of the world, if you want. And the circumference of the graph, this is another measure. So let me get back to this. So the measure of a diameter is a graph property, And the periphery is also a graph property. It involves vertices, but it characterizes a set of vertices that have this property in the graph. Okay. And what we call the circumference of a graph is again a graph property. It works in both undirected and directed graphs. The total number of edges or arcs in the longest cycle of the graph is the circumference of G. And so here in this directed case, I've highlighted the longest cycle, okay, in red. If you were to follow this, this would involve 6 jumps to get back to any of the vertices on the cycle. If you start from x2, for example, you follow along and you get there. So this is the circumference. And I believe this is the last one I will show you in this video. This is the girth. And the girth is the total number of edges or arcs in the shortest cycle. So where the circumference is the total number of edges or arcs in the longest cycle, the girth of the graph is the total number of edges in the shortest cycle. And here I've removed, just so that we don't have to worry about, by the way, I should have pointed it out before, I've removed the loops, and so to make it clear that we have a digraph. And here you see that the girth is 2, because I have a cycle of length 2 here. Now let me briefly move on to the R version. So I've prepared a very small example here, which is these graphs that we're considering. I'm looking at the graph here. I am looking at the graph from which I have removed the arrows. So this is exactly this graph. Of course, it's not organized exactly the same way. I'll point out, if you need, you could impose the position of the vertices. You can exactly say that vertex is going to be here, etc. I'm not doing this here. And so, for example, you can see that the two graphs, although they're the same, except for these loops, they don't look the same at all. The vertices have not been placed in the same place. I'll just show you the eccentricity, which is because I don't want to show you how to get these matrices, which, I mean, you're going to find out very quickly, but because it's the assignment, I'm going to skip here. And I'll just point out this is probably what you'll be looking for even when you're making that matrix. So in terms of eccentricity, I can compute the out eccentricity, the in eccentricity, and the eccentricity. And so this is giving you for each vertex, so there are 6 vertices from 1 to 6. For each vertex, it's giving you the eccentricity. So you can see this is 4. So this is the out eccentricity, and this is what I've plotted here. So this is 4, 3, 5, 5, 4, 4, which is indeed what we have in these this matrix. The in eccentricity, so the out eccentricity is the one we want here. The in eccentricity is the same thing, but we are counting in arrows instead of out arrows. And so some things change a little bit. The in eccentricity of 2 is much higher than the out eccentricity of 2. And when you do not consider orientation, well, when you assume that you can follow an arc as if it were an edge, then you have much lower eccentricities, which makes sense because, for example, from x3, I can follow things in a much, so I have from 3, I have a path of length 1 and a path of length 2, so the eccentricity is 2. Okay. Why is it not following that one? That's So that's interesting. I'll have to check what definition they're actually using here. So that's one of the problems with graph software, is that sometimes you really have to look closely at the definition. Okay, and I just wanted to show you this other graph also, which is the one that I've disconnected. And I'll come back to these example graphs as we're making way in this course, but I'll also have other graphs to show you. And I think this is it for this lecture.